السلام عليكم ورحمة الله وبركاته. Okay, let me share my screen. All right. Today we will begin to look at hydraulic structures. The intended learning outcome is the end of the presentation. Students will be able to understand how to use hydraulic structures to measure flow in open channel. By flow here, we simply mean discharge, flow rate, So some simple classification of hydraulic structures, we have this table 13.1 where we have the type, purpose, and structure. So for flow measurement structures, the purpose is to determine discharge. And normally we use weirs, orifices, flumes. Okay, all of this we'll look at in this chapter. I have already explained the importance of flow measurement, for any water resources development. Flow is one of the most important parameter, for any flowing water. Okay, because knowing the flow rate will help the engineer, design, for water supply to any town. Okay, knowing the flow rate of a river or stream or a given channel, okay, will help determine whether the quantity will be enough to meet the demands of the water demand of the community, as well as sometimes it can be drainage network, it can be flowing open channel that is draining a particular catchment. Okay, so knowing the flow rate will help determine the adequacy or otherwise of the channel to avoid flooding. So, and we have storage structures, flow control, or flow control structures, whose purpose are to. Okay, we have storage structures, purpose are to store water, and here we have dams and tanks. In Saudi Arabia, here we don't have the surface water resources is not so much. So maybe you have never seen a dam, maybe physically, okay, but sure, you all have tanks in your various residential houses, okay, which are used for storing water, both the underground tank as well as the overhead tanks. House here, has an underground storage tank and an overhead tank. Underground storage tank will be used to collect water from the water treatment plant, and then a pump is attached to the underground storage tank to pump water to the overhead tanks, okay, so that water will flow by gravity to all the various, toilets, kitchens, and all the wash hand basins and what have you. And then you have flow control structures, okay, which are used to regulate the quantity and pass excess flow, okay. This is for regulation of the quantity of flow. And here we have spillways, outlets, gates, and valves. Okay, we looked at some gates, in fluid mechanics. We may look at spillways are part of a dam structure. Okay, the dam, stores water. The part of the dam that allows excess water to be spilled over or to be passed over is called the spillway. So a spillway is an integral part of a dam. Okay? Then we have divergent structures. As the name implies, they divert the main course of water. And here you can also use dams, weirs, canal headworks, intake works, and what have you. For weirs, we are going to consider them in this chapter. Okay, we'll discuss about their hydraulics at length. And you have conveying structures which are meant to guide flow from one location to another. okay, or they are meant to, let's say, evacuate flow or to drain a given area. And here you have the, the open channels, deep, in the downtown Hasselblad, and you have these big open channels which are meant to drain the water, the precipitation that falls over the entire city, okay, to drain it away from the town and to avoid flooding. Okay, so you have open channels. Okay, and currently they are even building, some tunnels, that are mainly drainage tunnels. Okay, they will serve as they will be collecting all the precipitation from various parts of the town and will be draining to far outside, to an area outside the town. If you remember, some of you, we visited the construction of these drainage tunnels, which are being constructed currently around, that for the new market. Okay, and also you have pressure conduits, you have pipes, canals, and sewers. All these are conveyance structures. Okay, guide flow of water from one location to another. Okay, at the end in chapter 5 we'll look at pipes, and in the next chapter we'll look at open channels. That's the design of open channels. Okay, though even now we'll begin to look at some aspects of the open channel that is concerned with the weirs and flumes. Okay? And then you have collection structures. The collection structures, as the name implies, they collect water for disposal. Here you have drain outlets or infiltration galleries and wells. Okay, so they collect water for disposal or for onward transmission to another point. Okay, like wells. Wells, they collect water, from the aquifers, and then they are pumped for use. Okay, then you have energy dissipation structures. Uh, these are structures that prevent erosion and structural damage. You usually find them at the bottom of a steaming basin. Okay, the bottom of a steaming basin. Okay, and you have such tanks and dams. Okay, we talked about the surge tanks when we were discussing about in fluid mechanics in 233, when we were talking about water hammer. Okay, water hammer, that sound which is due to the compression of water. We mentioned that water is compressible, sometimes due to certain hydraulic phenomena. A water can be locally compressed to reduce, its density can be decreased. Okay, when it is locally compressed, it makes that sound like as if hammering the pipe. Okay, so to avoid, and this happens at sharp bends and some, sudden opening or closure of a valve. Okay, sudden closure of a valve is one of the main causes of surge. Okay, or compression, local compression of water in a network. So to avoid, because when surges occur, they sometimes they like impact the pipeline. They affect the pipeline through some structural damage. So we surge is not something that we want in a pipeline. Okay, we don't want water hammer to take place. Okay, so to avoid the occurrence of water hammer in our pipeline, we now use surge tanks. Okay, which are usually like reservoirs, open reservoirs, depending on whether if it is a huge pipeline like a penstock. Penstock is a large diameter pipeline, like for hydropower generation. So in such a case, water tower, in which water will not will avoid we will avoid the occurrence of water hammer in the penstock. Then for short pipelines, small pipelines, like the pipes for the water distribution network to in our buildings, uh, uh, we use a particular device, okay, which is just fitted along the pipeline, okay, to take care of the surge or to take care of the water hammer, okay. And that device is fitted, it has some gas inside, okay, which will help in taking care or absorbing the excessive pressure that is to be generated as a result of the water hammer. And then we have shore protection devices. Shore is the bank, bank of a river or sea. Okay, so shore protection devices here we have dikes, groins, jetties, revetments, breakwaters, and sea walls. If you go to the seashore, you will see the sea wall, some riprap, some stones, that are meant to protect the shores, okay, from erosion caused by the water hitting the embankment, by the water that will be hitting the embankment. Okay, and you have river training and waterway stabilization structures. Okay, and here their purpose is to maintain a river channel and water transportation. And the structures that fall under this, you have what is levees, cut-offs, locks, piers, culverts. Okay, here, but we know culverts. They are meant to maintain a river or a river channel and water transportation. And then we have sediments and quality control structures. Sediment is the debris. When water is flowing, most especially in line channel, which is dug inside soil, it carries along with it the soil particles. Okay, these soil particles constitute the sediment. Okay, they are the sediment. So sediments and quality control structures. The purpose is to control or remove sediments and other pollutants. Okay, so these sediments will affect the flow rate. They will deposit at the bottom. So they are unwanted per se. They are unwanted material in the water. They are unwanted materials in water. Fortunately, if we have a channel dug if we have an online channel dug in soil, definitely we will have sediment. And sometimes the sediment can come from other sources, not from the channel itself, but from the environment. Because when water is washed, from the surface of the catchment, they will all end up in the drains. Okay, and they will carry the sediment, and when the sediments are inside, they can deposit. Okay, depending on the volume, if they deposit at the bottom, they will reduce the effective size of the channel, and that will affect the flow of water in the channel. Okay, so this we can use racks or screens, traps, or sedimentation tanks. Okay, sedimentation tanks where the water will be collected and then allowed to settle, so that all the sediments will now settle down over time. Just like a flocculation, a sedimentation tank in water treatment plant, in which water is collected after coagulation. After you apply the chemical that will reduce the zeta potential of the flux, so that the particles, the sediments, can come together and become bigger. So you pass it over to sedimentation tank where the flux will now settle down. Okay, and the clear water will move away. Will move out of the sedimentation tank. Okay, so here we can have sedimentation tanks. We can also have filters as well, or sluice wells. And then we have hydraulic machines. Okay, we discuss hydraulic machines in also fluid mechanics, and they are used to convert energy from one form to another. Okay, and hydraulic machines here, basically we have pumps, turbines, rams. Okay, probably in chapter 15 under the water distribution network, we'll discuss about the pumps. Okay, and then for turbines, then it's beyond the scope of this course. Okay, so this is like a general overview of some of the hydraulic structures that we have, and each one of these structures has specific application. Okay, in our daily lives. Okay, in our daily lives, was controlling water, measuring the amount of water, and preventing damage to the surroundings. Okay, so under this chapter, we will look at some of these hydraulic structures, and then, of course, I will not permit us to look at each one of them. So we will look at some of the hydraulics involved in their analysis. Okay. Now, if you see the first one here, it says flow measurement structures. Flow measurement structures. Okay. Flow measurement structures, and the purpose of these structures are to determine discharge or flow rate. Okay. And one of them is orifice. We have weirs. We have flumes. Okay. So we will start with an orifice and then expand to weirs and then look at flumes as well. Okay? These are the commonest flow measuring structures. So an orifice, as the name implies, is just a small hole. Simple. Just a small hole. When you have water being retained, let's say this is a channel, okay, then you have a small hole where water is now flowing. Okay, this is like side view. If you want to look at, let's say, front view, let's say, you have a small hole where water is just jetting out. Okay, so water is jetting out from this hole, which is called the orifice. Okay, orifice is simply a hole. Very simple. Okay, so now flow through a small orifice. So we will derive the formula for flow through a small orifice, and more often than not, we'll be deriving the velocity of flow, because from the velocity we can easily get the discharge. Okay, because using the continuity equation, we know the velocity multiplied by the cross-sectional area of flow gives the discharge. Okay, so we'll be deriving the velocity of flow, and then to get the discharge, we simply apply the continuity equation. So when the area of an orifice is sufficiently small with respect to the size of the container, the velocity of flow can be considered constant throughout the orifice. Okay, so but what is the condition when the area is so small compared to the size of the container? So we have a constant velocity of flow. Okay, throughout the orifice. And for the orifice section in the in figure 13.1, we apply the Bernoulli's theorem at points 1 and 2, the datum at the center of the orifice. So the datum is at the center of the orifice. The center of the orifice. Okay, this is the center. So this is the datum. So we apply Bernoulli's theorem, okay, at points 1 and 2. You remember Bernoulli's theorem neglects the head loss. Okay, it neglects the head loss. So, and it simply states that Z1 plus the head plus the velocity head. So Z1 H1 is equal to Z2 plus H2 plus V2 over 2G, V2 squared over 2G. Okay. So if we look at it, this is the datum. Okay. All passing through point 1 and 2. So Z1 and Z2, 0. Okay. Then we have H1, which is equal to H. Okay. And H2 compared to H1 is small that it can be neglected. Okay, so that is why we neglected H2 and H was equal to H. Okay, and of course, the approach velocity V1 is very small compared to V2. Here, H1 when compared to H2, H2 is very small. Okay, the same thing here. The approach velocity here V1 is very small compared to the velocity V2. Okay, it will become very small because the flow rate is the same, AV. The flow area here is very high. The velocity has to be very low. While in this case, cross-sectional area of flow is very small, so the velocity has to compensate for that to ensure that the flow rate Q is the same. Okay, so that's why the velocity is very, very high compared to the velocity at this point. Okay, hence we can neglect the velocity, the approach velocity, V1. So that is why here, when we neglect V1 also, so we will have H to be equal to V2 squared over 2G. So V2 is now equal to square root 2GH. So the velocity at the orifice at this point is equal to square root of 2G times the head, before the orifice, upstream of the orifice. Okay. Now, this is the theoretical velocity. If you look at it, we neglected so many things. Okay, first we neglected the head loss, due to friction, and then we neglected the approach velocity, and then we neglected the head at the orifice. Okay, so definitely we made so many assumptions to simplify our computations. Okay, so this is more or less like the theoretical velocity. Okay, and then the actual velocity will be slightly less than this because we remove so many terms that would have, reduce the value of this velocity. So this value, this V2, is overestimated. By overestimated, it means it is higher than the actual velocity, if we were to go to the field and measure it. Okay, so the actual velocity is slightly less due to the viscous shear effect. This viscous shear effect, we talked about, the viscosity, which is like friction in liquids, and we have the frictional force also that is occurring between the liquid and the solid boundaries. Okay, so this viscous shear effect in the form of shear force, because shear force is also related to the friction. All these have been neglected, and all this will have impact on the flow rate, on the smooth flow of water or liquid. Okay, and all these have been neglected. Okay, as well as the orifice age. Okay, so including a coefficient of velocity, we have V2 equals CV square root of 2G. Yeah, so we introduce a coefficient to take care of all these assumptions, all these oversimplifications. Okay, so as our actual velocity will now be equal to coefficient of velocity times square root of 2gh. This coefficient of velocity definitely is going to be less than 1 because here we mentioned that the actual velocity is slightly less. So to make this value less, we have to multiply by a factor that is less than 1. If you multiply by a factor more than 1, then this value will be higher. It's only when we multiply by value less than 1 that the value here will be smaller. So the coefficient of velocity here is less than 1. Okay, it's less than 1. 0.8, 0.9, okay, depending on some factors that we will discuss later. Okay, and the coefficient of velocity, CV, is simply the theoretical velocity, the actual velocity over the theoretic velocity. This velocity V2 we obtained by, this simplification, we call it the theoretical velocity. It's theoretical because it cannot be obtained in practice. In practice, the value of the actual velocity is less than this value. Okay, so that's why we call it theoretical velocity. And this one, to get the actual velocity VA, we now multiply a coefficient of velocity times the theoretical velocity. Okay, and that is why here this is the theoretical velocity and this is the coefficient of velocity. Okay, so when we multiply them out, we have VA, which is the actual velocity. If we are to go to the field and measure the flow rate using any flow rate, measure the velocity using any velocity measurement instrument, we will get this value, okay, which is the actual velocity. Okay. So now the size of the jet is narrowest at a distance of about 1/2 the orifice diameter. Okay. The size of the jet is narrowest at a point 1/2 the orifice diameter. If this is the orifice diameter, about half the orifice at a distance that is like about half the orifice diameter, called vena contracta. Okay. You consider at this it is higher, and then it becomes compressed, and then it enlarges. Okay. At the narrowest section, which we call the vena contracta, the streamlines are parallel and perpendicular to the orifice. So the water flowing, you know, the streamlines, that line, the path taken by the individual fluid molecules or particles are parallel and perpendicular to the orifice. Okay. So then, so we can find the discharge at this point. Okay. So at this point, our discharge, remember, this is the velocity, V2, the actual velocity. So to find the discharge, Q, we just multiply by the area of flow, because Q is equal to AV. We already know V. V is CV square root of 2GH. So this is the area, AC, which is the area of the vena contracta. Okay, A subscript C. Okay. Now, in terms of the orifice area, we now introduce what is called the coefficient of contraction. Okay, because A subscript C, the area of the vena contracta, is less than the area of the orifice. Okay, so the jet is contracted. It is contracted, as you can see. The area here, cross-sectional area here, is less than the cross-sectional area here. Okay, so it is contracted. Okay, and we use CC to determine the coefficient of contraction. Okay, the coefficient of contraction, CC, is simply the area of the vena contracta over the area of the orifice. Okay, over the area of the orifice. So this is the coefficient of contraction. It gives us like a percentage, how much of the orifice area is contracted. Okay, is it by 90%, 100%, or even 0%? Okay, or even 0%. Because if AC is equal to A, then the coefficient of contraction will increase. Okay, it will tend to 1, which is 100%. So meaning there is no contraction. Okay, if the higher the value of the coefficient of contraction, the less the contraction. Okay, while the lower the value, the more contracted the jet is. Okay, higher values of CC indicate less contraction, because imagine CC equal 1, it means AC equal A, so there is no contraction. Okay, and by saying it's equal to 1, okay, it means it is 100%. Okay, now lower values, let's say 0.6, it means there is high contraction. Okay, it means AC is less than A, and that indicates there is contraction. Okay, so lower values of CC less than 1 indicates higher contraction, while values close to 1 indicates less contraction of the jet coming out of the orifice. Okay, so now from the AC now, AC is simply CC times A, okay, which is substituted here. We substituted AC with CC times A. Okay, so this is now the formula for the discharge. Okay, that is the product of the coefficient of contraction and the coefficient of velocity, where CC is the ratio of the area of jet at the vena contracta to the area of the orifice. Yeah, which is this formula. okay, and known as the coefficient of contraction. Now, instead of having two coefficients, it becomes, cumbersome in one equation. So the two coefficients are combined into a single coefficient of discharge, CD. So now, CD, the coefficient of discharge, simply coefficient of contraction and the coefficient of velocity. Okay, and the coefficient of velocity. Okay, because here we are measuring discharge. So Q is equal to CD A and square root of 2GH. Okay. The same thing here, CD, similar to my definition of CV. Okay. So CD now is now given by the actual flow rate over the theoretical flow rate. Okay. So the actual flow rate will now be the coefficient of discharge times the theoretical flow rate. Okay, so this Q gives the actual flow rate, okay, which is the flow rate that if we are to carefully control the flow rate here using any machine or to simulate in the lab, using any pump in which we can know exactly what the flow rate is, okay, and if we are to measure this height and substitute, and maybe if we know the coefficient of discharge, then the two values will agree. Okay. Now this is, if you remember, for small orifice. Okay, small orifice. And what did we define small orifice? Where the area of an orifice is sufficiently small with respect to the size of the container. What about when we have large orifice? Flow through a large orifice. Okay. Now, when the head over the orifice is less than 5 times, the size, that is the diameter or height of opening, the diameter or height of opening of the orifice, it is a large orifice, okay, for which the previous equation for small orifice is not true, okay? And here it says if the head over the orifice is less than 5 times, the head over the orifice is H, is less than 5 times the diameter or height of the opening, okay? The head, if we call this H1, less than 5 H2, okay? H2 is the height of opening at the orifice of the orifice. So if the head is less than 5 times, okay, is less than 5 times this, meaning the head is not so much compared to the height or opening of the orifice, then the streamlines are not normal to the orifice plane and the velocity is not constant throughout the orifice. If you remember, here we said the streamlines of this vena contractor are parallel to the cross section, okay? Are parallel, okay? So the streamlines are parallel and perpendicular to the orifice, okay? That is when you have H to be very high compared to the opening, okay? If this H is not very high, it's not so big compared to the height of the opening, then the streamlines will no longer be perpendicular to the orifice, okay, and the velocity will no longer be the same at the orifice. So what do we do now? So instead, it acts like a weir, okay, it acts like a weir under pressure. A weir is simply, a structure placed across the path of a flowing fluid in a channel, stream, or river. We are going to discuss more about weirs, okay? And I think even in last week, we started discussing about weirs when we discussed about broad-crested weir. We briefly discussed about broad-crested weir. And After the orifice, we'll look at mouthpiece, and then we'll look at weirs as well under this section. So we will discuss extensively about weirs. Okay. So it acts like a weir under pressure. Okay, with the water level always above the top edge of the weir. Okay, with the water level always above the top edge of the weir on the upstream side. Now, in the rectangular orifice under the low head shown in this figure, this is an orifice. The width is B, okay, the height, okay, and you have this, okay. This is H1 from the bottom of the orifice to the top of the water. This is H2, okay, from the top of the weir to the top of the water level. Okay? And here so in the rectangular orifice under the low head shown in this figure, the velocity of flow through an elemental strip at a depth h from the free surface is 2gh. Okay, when you consider an elemental strip here, a small element, okay, delta h of water coming out of the orifice, okay, the velocity of this small element will be given by the flow or by the velocity which we found for a small orifice, which is square root of 2gh. Okay, and the discharge, which is dq, because we are considering small element, okay, so the discharge will be dq times the area. The area is going to be b times dh, which is the height. Okay, so here we need to integrate for total discharge. Okay, so for the total discharge, we need to integrate between the limits h1 and h2 and introduce coefficient, because here we need to integrate between the height of the orifice, and the height orifice is given by h1 minus h2. Okay, so we need to integrate between h2 and h1. Okay, so when you integrate this, okay, from h2 to h1, okay, you'll arrive at this. Okay, it's simply, you know, b is constant, square root of 2g is constant, the integral of power of half dh. Okay, you add 1 to the power and divide by the new power, so it becomes h to the power of 3. So this becomes 2 over 3 b root g h to the power of 3 over 2. And then you now substitute the limits. Okay, you now substitute the limits. h1 from h2 to h1. Okay, so that's why you have it here, h1 minus h2. Okay, and of course, because we want the actual flow rate, that's why we are introducing the coefficient of discharge. All the time, when we don't have the coefficient of discharge, it means the flow rate is simply a theoretical one. Okay, when we want the actual one, the actual flow rate, we need to introduce the coefficient of discharge. Okay, so this is now the flow rate, the total discharge for a large orifice, okay, which has been treated more or less like a weir under pressure. Okay, a weir, like I said, is simply you have a channel, then you have, let's say, rectangular weir, so water will be flowing over it. Okay, we will look at the different types of weirs, and we will see that the equation of the flow rate is something similar to this one as well. Okay. Now, for a circular or any other shape of orifice, because this we consider like a rectangular one, okay? So for a circular or any other shape of orifice, the area in equation A is expressed in terms of h, okay? And then the equation is integrated. This is the area, isn't it? This we considered a rectangular area. So for any other shape, is it triangular, trapezoidal? So you express the area in terms of h, okay? And then you integrate. If the velocity of approach cannot be disregarded, you see here we are neglecting the velocity of approach. If you remember here, we disregarded the velocity of approach, isn't it? Okay, so if the velocity of approach cannot be disregarded, then we need to add the velocity of approach. We need to add v squared over 2g should be added to both h1 and h2. Okay, v squared over 2g, which is the velocity head. Okay, should be added to both h1 and h2. So meaning in the integration here we have h1 plus v squared over 2g, and this one also h2 plus v squared over 2g. Okay, and the same thing here, these are going to change now. Okay, these are going to change. Okay, so here they will include h1 and h2 too. They will both include the velocity of approach. Okay, now let's look at a simple problem here. It says in a stream of 5 feet width and 3 feet depth. A stream of 5 feet width and 3 feet depth, a plate is placed that has a rectangular orifice. Okay, let's try to sketch this so that we can understand the problem very well. You have a stream, 5 feet width and 3 feet depth. So this is 5 feet width and 3 feet depth. Okay, a plate is placed that has a rectangular orifice, 3 feet in length and 1.2 meter depth in height. The upper edge of the orifice is 9 inches below the water surface. Okay, so the upper edge of the orifice is 9 inches below the water surface. This is 9 inches is less than 1 feet, isn't it? Because 12 inches give 1 foot. Okay, so this is where the orifice is. The orifice is rectangular and it is 1.2 feet. Okay, and the length is 3 feet. Okay, so this is the orifice. Now we are to determine the discharge, determine the orifice discharge. A, treating it as a small orifice, and B, using the large orifice approach. The coefficient of discharge is equal to 0.6. Okay, the coefficient of discharge is equal to 0.6. So for the first one, to determine the discharge, the discharge is CD A to GH. Okay, now let's analyze. Okay, what's our H? H is the head of water, the total head of water from the water surface, isn't it? From the water surface to the middle of the orifice, isn't it? To the midpoint of the orifice height. Okay, so the midpoint of the orifice height, the total height of the orifice is 1.2. So the midpoint from here to here is 1.2 over 2, which is 0.6 feet plus 9 inch. So it is going to be 0.6. 0.6 is obtained from by dividing the height, the total height of the orifice, which is 1.2 feet over 2. Okay, and then plus the 9-inch, which is the distance from the top of the orifice to the water level, 9-inch. Okay, so 0.6 plus 9-inch is 9 over 12 feet. Okay, so which is 0.6. 9, this is 0.75. Okay, so this is how we obtain 1.35 feet. Okay, so water depth to orifice center, 1.3, which is our h. Okay, and this is equal to h. Okay, what about the area of the orifice? Simply the area is 3 by 1.2 feet. Okay, so 3.6. And then we go and plug in these values in the formula for the actual discharge. The coefficient of discharge was provided to be 0.6, and then we have our h, which is water depth to orifice center, 1.35. Then we plug in, okay, g, because we are using the English unit, that's 2.2, okay, and then this is the flow rate, 20.14 cubic feet per second. Is it clear? Now, the next aspect, because the first part says treating it as a small orifice, and B, now using the large orifice approach. Using the large orifice approach. The large orifice approach, we have H1 and H2. If you look at this figure, okay, H1, the distance from the water surface to the bottom of the orifice, H2 from the water surface to the top of the orifice. Okay, so what is our H1 and H2 in this case? Okay, H1 from the top of the water surface to the bottom of the orifice. Okay, this H1. Okay, and this is simply 9-inch plus 1.2. Okay, 9-inch plus 1.2 feet. Okay, 9-inch is 0.75. Okay, plus 1.2, which is 1.95. Okay, and what is H2? H2 from the top of the water surface to the top of the orifice, which is 9-inch. 9-inch is equal to 0.75 feet. 0.75 foot. Okay, and then we use the formula. We just go and plug in into this formula. This one. You know, our H1, H2, B, C, D. So we plug it in, plug the values and calculate. We have the value of the flow rate to be 19.96. So you can see when we treat it as a small discharge, as a small the 19.96. Okay. Now, if we want to include the velocity of approach now, okay, this is more or less this. In the first one, we neglected the velocity of approach. Okay, we neglected the velocity of approach. Now, if we want to include the velocity of approach, we use this Q to find the velocity of approach now. Okay, which is simply V equal Q over A. Okay, V equal Q over A, and this is V1. Okay, so the area with the area of the channel, which is 5 by 3. Okay, so this is the area, which is in feet per second. The velocity is in feet per second. The velocity of approach, and then we calculate the velocity head, which is simply V squared over 2G. Okay, so this is the velocity head, and then we now include the velocity head. Okay, we now include the velocity head. Okay, so including the velocity head, now we have, because including the velocity head, simply what we will have here, H1, it will be H1, it will be H1 will turn into H1 plus V squared over 2G. We add the velocity head. Same thing with H2. Okay, it will be H2 plus the velocity head. Okay, so this is the velocity head, 0.03. So we add the velocity head to H1 and H2. Okay, so they become, instead of 1.95, it becomes 1.98. Instead of 0.75, it becomes 0.78. And recalculate the flow rate. Okay, so you can see when we include the velocity head, our flow rate increases slightly. our flow rate increases. Okay, it moved from 19.96 to 20.2. Although you can see that the increase is so small because 19.96 is approximately equal to 20, and 20.2 is also approximately equals to 20. Okay, but this is the way in case you'll be asked to include the velocity head. Okay, the first one is when we neglect the velocity head. When we neglect the velocity head, it gives us 19.96 cubic feet per second. While if we include the velocity head, which is more realistic, okay, we now have 20.2 cubic feet per second. Okay, is it clear? Let's have a short break and then we will start to talk about mouthpieces. Okay. Today only 11 guys are around, so 2 are missing. Oh, one also just left. So I hope those 2 that are missing will not miss today's major midterm lab. Today we have midterm lab. Don't forget. Okay? We have 11 guys. Oh, 12. Okay. So someone came back. During the lab, it will be held in the computer lab 04110, the computer lab. Okay, 04110. First group will start exactly at 2, and then the second group exactly at 3:20. Okay. Yes, at 0410. Okay, let's continue. We will take the exam at the same time in the computer lab. So all the groups, group 1 and group 2, will be there. The lab is big, you know, we have over 28 systems, so we can ensure social distancing. Okay. And one of you guys is missing now. Who is absent? So that please let him know. Make sure you pass the information to him so that he doesn't come after the exams or come late. Okay. I'll also post on our WhatsApp group. So let's move on. We just finished discussing how an orifice can be used to measure flow rate. Okay. Now we have another hydraulic structure called mouthpiece. Okay. A mouthpiece has a length of 2 to 3 times the jet diameter. Okay. It is used to increase the coefficient of contraction. I told you before, you know, when you increase the coefficient of contraction, what happens? When you increase the coefficient of contraction, the flow rate increases, isn't it? But when the coefficient of contraction is reduced, then the flow rate is reduced accordingly, because the coefficient of contraction is simply the area of the vena cava over the area of the orifice, isn't it? So, and when it is increased, remember, CC, simply AC over the area of the orifice. Okay. So higher value of CC, okay, means that the area of the vena cava is getting closer to the area of the orifice, okay, and that will increase the discharge, because the discharge is CC CV area times 2GH. Okay, so when this increases, the discharge, the actual discharge increases as well. Okay, so the mouthpiece is used to increase the coefficient of contraction, CC. Okay, and a mouthpiece is used to measure discharge, okay, by applying this equation. Now, the mouthpiece is just, we will see the different classification, okay, and then we will see the figures as well. Mouthpiece can be classified based on the basis of position, okay, and in this case, we have internal and external. Pipe, for the internal, pipe is fixed inside the tank or vessel. An external pipe is fixed and projected outside the tank, the tank walls. For the internal, it will be something like this. Oh, yeah, you have the orifice, and you have a pipe inside, okay? So water will be flowing, okay? Flowing outside, okay? Understand? And the length of the pipe is what? 2 to 3 times the jet diameter. This is internal. And for the external, pipe is fixed and projected outside the tank walls. So for the external, it is going to be like this. This is the orifice, and then you fix a pipe, a horizontal pipe, okay? And then water now flows through and out of the pipe wall, okay? Now, for the flow pattern, this is one of the classification, internal and external, on the basis of position, okay, whether the pipe fix is internal or external. The second classification is based on the flow pattern. Here you have running free and running full. What do you mean by running free? When the water jet, after contraction, a mouthpiece does not touch pipe internal walls, okay? This E is going to be removed. Okay. There is no E in touch. I will correct it. Okay. So running free is when water jet after contraction, okay, the mouthpiece does not touch pipe internal walls. And the other one is water jet after contraction in mouthpiece touches pipe internal walls. What are we saying? In the first case, when you have the pipe, water jet is contracted, but then after contraction, the water jet did not touch pipe internal walls. Okay, this is why it is contracted. So the water jet just come out without touching the pipe internal walls. Okay, definitely this type will have less, the coefficient of contraction here will be less compared to the running full. Running full is the water jet after contraction in mouthpiece touches pipe internal walls. So in this case, when you have the mouthpiece, water after contraction touches the mouth pipe internal walls and then comes out. Okay. So in this case, the coefficient of contraction here is less, the coefficient of contraction here is higher because the water jet now fills all the space of the mouthpiece, okay, as it is coming out. Is that clear? So the flow rate in the second case will be higher than the flow rate in the first instance, okay? So running full will be better than running free, okay? So this is classification based on the flow pattern. Now, another classification, which is the third one, based on the shape of the mouthpiece. Okay, you can see that there is contraction here, CC, and then the water jet now touches the walls of the mouthpiece. Okay, and then that will increase the flow rate. The coefficient of discharge here will be higher. So based on the shape of the mouthpiece, we have cylindrical external mouthpiece. Okay, cylindrical. This is cylindrical and it is external. Simple. So here the vena contractor occurs at a distance of half the orifice diameter from the outlet of the orifice. In an external mouthpiece of a length 2.5 times the diameter, the vena contractor will occur within the tube. This is the vena contractor where the contraction occurs. And the tube will be full when discharge takes place. So it is full because after the contraction, the water molecules are touching the sides of the mouthpiece, okay, which makes CC equal to 1. So the coefficient of contraction here is equal to 1 because the area of the contraction is, because here we measure the area of contraction at the end, okay, is equal to the area of the orifice. This is the area of the orifice, okay. This is the area of the orifice, okay. So this is the area at the end, okay. So if they are equal, this will approximately equal to 1. In practice, you may not get exactly 1 because you still have shear stress, frictional force acting, okay, but it will be maybe 0.98, 0.97, which is approximately equal to 1, okay. But then there are turbulence losses that will reduce the coefficient of velocity, okay. We have the velocity here, so turbulent losses will reduce the coefficient of velocity, but the coefficient of contraction will be almost equal to 1, okay, in this case. Now, another one is the convergent outpiece. As the word implies convergent, so it is converging. If you have an orifice, you have the mouthpiece like converging, okay? Converging, meaning cross-sectional area is reducing with distance, okay? So, and then water will be jetting out. So the losses due to sudden enlargement can be avoided because when you have sudden enlargement, we will look at the other one, divergent and convergent mouthpiece, okay? When you have sudden enlargement, you have losses. You have huge losses as a result of sudden enlargement. Okay, so these losses can be avoided with a convergent mouthpiece. The discharge coefficient could even be equal to 1. Okay, the discharge coefficient also in this case could even be equal to 1, depending on how it is tapered. Okay, the discharge coefficient, which is CD, okay, even be equal to 1. This is a mouthpiece whose area decreases towards the outlet. You can see the area is decreasing towards the outlet. The inner profile of the mouthpiece almost matches that with the jet. Okay, no sudden enlargement of the flow section occurs, and hence there will be no loss of energy head because there is no sudden enlargement. Sudden enlargement leads to energy head loss. Okay, and the area of the jet is simply the water coming out. Okay, so the area of the jet at outlet is the same as that of the mouthpiece at outlet. Okay, hence you have high value for the coefficient of contraction. Hence the coefficient of velocity and coefficient of contraction are all unity because of the fact that the area of the jet is the same as the area of the mouthpiece. Okay, so the coefficient of contraction becomes unity and the coefficient of velocity becomes unity, which means the coefficient of discharge becomes unity as well. However, in actual condition, like I mentioned before, a small loss of head occurs due to friction. So the coefficient for discharge, the coefficient of discharge is 0.97 to 0.98. Okay. So 0.97 to 0.98, which is still approximately equal to 1. Okay, so you can see with the use of the mouthpieces, they increase the coefficient. Overall, they increase the coefficient of discharge, which in turn increase the flow rate. Okay, which in turn increases the flow rate. Okay, and this is another mouthpiece, which is the divergent Obel mouthpiece, which is also called divergent convergent mouthpiece, or convergent divergent, because it first converges and then diverges. Okay, but at the end it is diverging. Okay, so this mouthpiece is convergent until the vena contractor. This is the vena contractor. Okay, the coefficient, and then diverges. It diverges, meaning it opens up, the cross-sectional area increases with distance. So the coefficient is close to 1. For divergent conical tubes, a coefficient of discharge of more than 1 has been reported. Okay, that is for conical tubes. Okay, a coefficient of discharge of more than 1 has been reported. Although hardly do you find the coefficient of discharge becoming more than 1. Okay, Breta and Kane have provided a detailed discussion on orifice coefficients. So you can see here, this is the vena contractor. Okay, it contracts and then it diverges at the end. Okay. Now the fourth one is the reentrant or border mouthpiece. This mouthpiece projects inside the container, which is like the internal one. It projects inside you remember the first one based on position, which I said internal and external. So it projects inside the container. When it can run free or full. Okay, it can run free or full. When running free, it means that the jet doesn't touch the top of the mouthpiece. Okay, so definitely the coefficient of discharge here is less. Okay, when running full, means it is contracted, but then it touches the side of the mouthpiece. So at the end, it emerges at the same area as the area of the mouthpiece. Okay, so the coefficient of contraction here is higher than this one. Okay, it's higher than this one. Now, these are some the coefficient of discharge. For rounded orifice, CC equals 1, CV 0.98, and CD 0.98, which is good. So we'll have good discharge using the rounded orifice. For sharp-edged orifice, the coefficient of discharge contraction 0.61. Okay, this one 0.98, and this is 0.6. So this one will have less discharge compared to the rounded orifice. Now, for the external mouthpiece, you can see for the external mouthpiece 1, convergent mouthpiece 1, divergent mouthpiece 1, border mouthpiece. When it is flowing full, it is 1 also. So they all increase the coefficient of contraction. Okay, the coefficient of contraction is all increased. What about the coefficient of velocity? In this case, for the convergent is 1, for the divergent is also 1. For the free here is close to 1.98. And that will in turn increase the coefficient of discharge, which is the product of the coefficient of contraction and the coefficient of velocity. See the coefficient of discharge now. This is 1, this is 1, this is 0.8, and this is 0.75. And like I told you, the full is better than the free, which is okay. Yeah. So the flowing full is better than having free. Okay, in which after the contraction, the jet doesn't touch the sides of the mouthpiece. Okay. We discuss about orifice, then we move to mouthpieces, which are simply some attachments that can be installed at the orifices to increase the discharge. Now we move to weirs, which we also called notches. Weirs and notches are synonymous. Okay, and they are also used to measure flow rates, similar to orifices and mouthpieces. Okay, so water flowing in rivers and streams has to be monitored to ensure the adequacy of water supplies for municipal and industrial uses. This I explained in the previous class and even today at the beginning of the class. So weir is simply an overflow measuring structure which is built perpendicular to an open channel flow direction to measure the rate of flow of water. Okay, you just built it perpendicular to flow direction. Okay, to measure the rate of flow. And the weir notch is also called the overflow section. Okay, the weir notch is also called the overflow section. It is the opening through or over which the water flows. That is the particular exit where the water exits the weir. We call it notch. At the same time, we call it the weir itself. Okay, so sharp crested or thin plate weir has a vertical flat plate with a sharpened upper edge, and the water does not contact or cling to the downstream weir plate but springs clear. What are we saying? If you have water now flowing, okay, this is the sharp edge. Okay, so water is flowing over it. Okay, water is flowing over it, and it doesn't cling to the downstream weir plate. So water doesn't. This is the downstream weir plate. Okay, so but springs clear. Okay, so it springs clear. So this is the sharp crested. Okay, because the top of the crest is sharp. Okay, and here atmospheric pressure is maintained. Above it, atmospheric pressure is also maintained. It may have a solid broad section or concrete or other material. Okay, then it is known as a broad crested weir. That is if it has a solid broad section of concrete or other material. You remember in our previous class we looked at a broad crested weir, which is placed along a flow channel and water flows over it. Okay, so this is because this is broad, the solid broad section. Okay, and you can have one in which thin cross section. Okay, thin section, not broad. Okay, so this is broad crested weir. Because the crest is broad, water flows all the way from here to here. Okay, imagine one inch water just flow over it on the top, this one. Okay, so this is sharp crested weir. Okay, and this one in which the crest is broad, meaning large or spread, bigger. So we call broad crested weir. Weirs are classified according to their shapes. Okay, that is rectangular, triangular, trapezoidal, and parabolic. Okay, so we have rectangular, we have triangular, which we call the V notch, and we have trapezoidal. One of them, a specific type of the trapezoidal, we call it Cipolliti, and parabolic. We will show the diagrams for most of this in the subsequent slides. The rectangular weir is the most popular. Okay, it is the most popular, the rectangular weir, and a rectangular section that spans the full width of the channel is known as a suppressed weir. If you have the channel, yeah, and you install a rectangular weir that spans the full width. This is the full width of the weir is equal to the width of the channel. We call it suppressed weir. If the width of the weir section is less than the width of the channel, it is a weir with n contractions. And here you can have it this way. Okay. Okay. So here the weir, the length of the weir, the length of the crest is not equal to the width of the channel. So this has both end contractions. You can have just one end contraction or both end contractions. Okay. Where the downstream water level is lower than the crest, the downstream water level is lower than the crest, like in this case, the downstream water level. This is the weir crest. Okay, this is the downstream water level. It's lower than the crest. Weir is said to have a free discharge. If the downstream level is higher than the crest level, it is known as a drowned or submerged weir. So this, it has a free discharge. If the downstream water level is higher, it means it is submerged, isn't it? It is submerged, meaning it is drowned. It's like underwater. The weir is completely drowned. Now, with these figures, things will become clearer, all the explanations. This is like a section of the weir. This is suppressed weir. You can see the weir crest, the length of the crest is equal to the width of the channel. Okay, but in this case, for contracted weir, the length of the crest is less than the width of the channel. So this is weir with end contractions. And here we have two end contractions. We can have one end contraction or two end contractions. This one has two end contractions. And this is a V notch or triangular weir. Okay, you can see it, yeah, water flowing. And then this is free flow. Okay, flow over a sharp crested weir. You can see where it's not, this is the weir, sharp crest, and it's not touching the downstream side, not touching the downstream side. Okay, so it springs clear. Okay. Here you have air, which is atmospheric. Okay, this has to be maintained, and this is the head of water above the weir upstream. Okay, this is for broad crested weir. This is sharp crested weir, and this is broad crested weir. You can see the crest. Okay, the water has to touch the longer part of the weir. Okay, it has to flow over it before it becomes discharged. And flow over sharp crested weirs. The falling sheet of water which springs clear from the weir plate is called the nappe. This is the nappe. Okay, the falling sheet of water that springs clear of the downstream side of the weir. This is what we call the nappe. The falling sheet of water which springs clear from the weir plate. Okay, and when a sharp crested weir allows free access of air under the nappe, free flow or free discharge is said to occur. When we have air here, this is for free flow, okay, or free discharge. Free flow is said to occur. Free discharge must occur before a sharp crested weir can be used as a discharge major structure in an open channel, meaning we have to ensure that the water springs clear, emerging from the top of the weir, springs clear, has free access of air under the nappe. Okay, this is one of the conditions. This will emphasize when doing the lab. Our next lab next week, we will start to work with some weirs. Okay, with free discharge, head measurements at one upstream location enables discharge computation if the weir size and shape are known. Okay, a relatively large head is required for free flow to occur. Okay, so a relatively large head is required, meaning the upstream head, this one. Okay, large head is required for free flow to occur, so that the water will not cling to the weir face. Okay, because if the water is to the weir face, this will not be under atmospheric pressure anymore. Okay, and it will unnecessarily increase the flow rate. Okay, so we need to ensure that there is air trapped here. Okay, the pressure there has to be atmospheric. And in the lab, we are going to see how that can be maintained, how that can be achieved. Now, air is entrapped between the lower nappe surface and the downstream Hello guys.